The question reads, there are 168 prime numbers that are less than 1,000. Okay, well, prime numbers are quite interesting, very enigmatic. In other words, not much is known about prime numbers. They've been baffling mathematicians for centuries, millennia, because there is no pattern. See, there's no pattern to say, if I know that some number is a prime number, what is the next prime number? That question has not been able to be answered. All right, so therefore it's a rather erratic set, but somebody has actually counted the number of prime numbers, which are less than 1,000. They've come to the conclusion that there are 168 of them. Okay, you are given 5 options for their sum. Oh, all right, so you are going to add all these prime numbers, and S is the sum. Let's give a name. S is the sum of all numbers less than 1,000. Okay, this is, you are given 5 options for their sum, and only one of them is correct. Which is the correct answer? This is quite a question, because we don't know what the primes are. And there are 168 of them, and you need a computer to identify them, A and B, to count them. But now we are asking, which is the correct answer? But you are told that one of these is the correct answer. So can we logically deduce which one it is? Let's see, one important fact is 2 is the only even prime number. It's a very important fact. It's used often, prime number, in these problems. Because any number which is even can't be prime, because it's 2 times something. All right? So the only, apart from 2, every other number, prime number, has to be odd. Has to be odd. Okay, so you've got, therefore, amongst these 168, you got S is the sum is equal to 2 plus you got 167 odd numbers. All the other primes have to be odd. Now, if you add any 2 odd numbers, the sum of n odd numbers is even if n is even. Sorry, make so many mistakes while writing. You see, if n is even, the sum of 2 odd numbers, odd plus odd, is always even. So if you got 4 odd numbers, you're going to group them into 2 sets of 2 odds, and you'll have even plus even. In fact, if you got an even number of odd numbers, the sum is even. Right? So this is what I'm saying here. The sum of n odd numbers is even if n is even. and odd, if you got an odd if n is odd, what's the reason for that is, you see, you can write these 167 prime numbers, for instance, P1 plus P2, let's call them like that, 167. And then you group them in pairs, P1 plus P2 plus P3 plus P4. These are, I'm giving names to the prime numbers, the 167 prime numbers. And in the end, you got an odd number there. So in the end, you will have P165 plus P166. And then you'll have the 167 is left out in the cold. Right? So these, sum of two odd evens are all even. So these are all even. And you got several even numbers added together. So you're going to get an even, right? But this is odd, right? So you got even plus odd. So this has to be odd. Right. So in other words, you got S is 2 plus an odd number. So what I did here was calculated this sum of these odd numbers, and I saw it was going to be odd. Now, 2 plus an odd number is odd. So S is odd. So the sum that we're looking for is an odd number. Did I clear everything? So we've got 5 choices. So the sum will have to be an odd number. So this has to be eliminated. That's to be eliminated. Therefore, S is one of 11569, 76127, and 510, 513, 510,513. Now, I'm going to use a fact about the sum of consecutive odd numbers. Now, notice that it's an important fact. The sum of the first n odd numbers is n squared. Now, I think by the time you've got to where you are now, to look at these kinds of problems, this should be quite well known. Right? You can apply the arithmetic's formula, series formula to get to this. Easy to see. The first sums are 1 plus 3, which is 4. That's 2 squared. 1 plus 3 plus 5, that's 9. That's 3 squared. 1 plus 3 plus 5 plus 7, 16, 4 squared, and so on. All right, so if I take the first 500 odd numbers, 1 plus 3 plus 5, all the way up to 999, right? This is the sum of the first n odd numbers. This is actually equal to the 500 of them. So 500 squared, and that is 250,000. 25 with 4 zeros behind it. So this obviously, the sum of all the prime numbers, all the possible prime numbers, will have to be much bigger than this, because these numbers here, they occur at every alternate number, right? You have this odd, this odd, this odd. and so on. You have 998 and 999, which is odd. So you got almost half the numbers, 500 of them, they add to 250,000. So these 168 prime numbers should be very much smaller than this. So the sum of the 168 prime numbers because the odd numbers are coming from here, you see, right? 167 odd numbers. So this is greater than 250,000. I'm sorry, less than 250,000. Because those 167 odd numbers are coming from here. And that is definitely smaller than the sum of all the possible odd numbers. Right? You can add 2 to it, but it hardly makes a difference. Okay, so this 510,000 can be eliminated. Okay, because that is more than 250,000. Okay, so that now leaves us with the answer is either this is eliminated. The remaining two odd numbers are 11,569 and 76,127. Right? Now, at this point, I'm going to do a little bit of hand waving. You see, this 11,569 is less than 12,000, which is 20 times 600. And that is less than you see, now at this point here, I'm going to say that it is highly likely that there are more than 20 prime numbers greater than 600 and less than 1,000. You see, you got 400 consecutive numbers in the slot. And amongst those 400 numbers, you can expect the number of prime numbers to be more than 20. Now, I can't prove that, but I don't know if there's, I don't know any other way of justifying this. But one can list the primes here, and it's not easy to do that. And we can find 20 prime numbers which are in the slot here, whose sum is greater than 12,000. Right, which means that this is less than Yeah. So what it means is that hence S, which is the sum of all the prime numbers, including those from 600 to 1,000, it must be greater than 12,000, which is 20 times 600. You see, every one of these 20 prime numbers here are bigger than 600. And therefore, the sum of those 20 prime numbers will be bigger than 12,000. So the sum of, and this is just the sum of the prime numbers from 600 to 1,000. So the whole lot will be greater than that, which says that, therefore, we can eliminate this one here, 11,569. So this can be eliminated. Therefore, the answer is, okay, this thing is, I must admit, this is somewhat incomplete. Because we are saying that, making the assumption that there are at least 20 prime numbers between 600 and 1,000. And that can be proved, but you have to know, you have to identify 20 prime numbers. Okay, that'll take a bit of time. Try to look for the 20 prime numbers which are close to 1,000. See, and I think even if you come to all the prime numbers from 900 to 1,000, you probably will get the sum to be greater than 11,569. Anyway, so that takes care of that problem somewhat. Okay, and I come to the same answer, and it's exactly the same uh, method. Okay, let's go to question 9. Now, question 9 reads the following. A triangle with sides A, B, and 6 has area 4, B, C, and 6 has area 5, and with sides D, A, and 6 has area 13, and the area of the triangle with sides C, D, and 6. So you want to know what the area of that is. Now, when you try to draw this, I'll find that since you got 6 occurs in all the 4 triangles, right? It seems to me that it's going to be, your diagram is going to look something like this. And then you got a point in between. See, 6 occurs in all 4. So let me just draw a quadrilateral with all 4 sides equal to 6. Diagram is very inaccurate. We'll come to that just now. And then if you got a point inside here, we can get all these 4 scenarios in this diagram here. You should see just now. And if you take A, B, and 6, for instance, there's A and B. This is a triangle with sides A, B, and 6. And the area of this is 4. Okay, so that takes care of that. B, C, and 6 as an area of 5. So you got B, C, and 6 have got an area of 5. B, C, and 6 got area of 5. We finished off with that. And D, A, and 6 as area 13. So this is D. So D, A, and 6 as area 13. So you can draw a picture like this where you've got 6. Right, and as all the sides of this figure. But there's only one figure. The only quadrilateral with all the sides equal is a rhombus. Okay, why is that so? Because if you got a figure with the opposite sides parallel equal, any figure which has got this situation, that figure has to be a parallelogram. The reason is you can join this. Now you got this equals this equals this. It has to be parallelogram. When you join it, then these two triangles are congruent because you got 3 sides, which means that that angle which is opposite double stroke must be equal to this angle which is double stroke in this triangle. But these are alternate angles. Right? From that you can conclude that these lines are parallel. If you got a pair of alternate angles are equal, then the lines are parallel. And likewise, if these two triangles are congruent, as we said, this angle is opposite a single stroke, and in this triangle, the angle opposite a single stroke is that. But now these are alternate angles for this lot. So these two lines have to be parallel. So therefore, this figure has to be a parallelogram. Because these two are equal, these two are equal. So it has to be a parallelogram. But a parallelogram with all the sides equal is a rhombus. So, right? Could be a square, but a square has got one more property that all the angles are 90 degrees. Yeah, nothing is said about what the angles are, but the best we can say is all the sides are equal, and therefore it's a rhombus. So it's going to look something like that. Okay, and so now you have a situation. I do this using my drawing kit, but it's all, I can't make it empty. Anyway, so this is what you've got. You've got a point inside here, and the areas are, okay, let's put it this way. You've got a point inside here, you got the opposite, you got 4 triangles. Now, let's try it like the way I've got it here. I thought I might be able to use this tool, but it's becoming more confusing. Let me draw that, draw that. So it's a rhombus. I made the first side too big. All right. Now, this is a favorite trick. If you got, in any parallelogram, if you got a random point, and if you join that point to the 4 vertices, if you do enough problem solving exercises, you will see that this occurs sometimes in a Olympiad. So a useful fact to know that when you got any parallelogram and you do this, then it turns out that you can say something about the areas. A plus B, A and B, C, D, these are the areas. You'll always have that A plus B equals C plus D. The triangles opposite opposite each other, that sum of those areas is the same as the other sum. And the reason for that is you can draw through this point here. If I draw a parallel line, one parallel line, then I get that this triangle C it's got the same base as this parallelogram. This is parallel. The construction is that these are parallel. So this four-figure picture here is a parallelogram. And this triangle here has got the same base and between the same parallel. Its area is half the area of the parallelogram. So C is half the area. Likewise, D is half the area. So therefore, C plus D will be equal to half the area. So D is half the area of this parallelogram. And if you add these two parallelograms on the either side of the red line, you're going to get the full parallelogram. So therefore, C plus D will be half the area, one half the area of the full parallelogram. So if C plus D is equal to one half the area, the remaining part, A plus B, is also equal to one half the area. So that is why both of them are equal to one half the area, and you have that conclusion. So now in this situation here, you can see I've got a parallelogram here. So you got this area. We are looking for what is the area of the triangle with sides C, D, and 6. I should have asked that question. This C, D, and 6. What is X? So that is the question that is asked. And from what I just said now, the X plus 4, and those two will add up to those two, 13 plus 5. Right? And that's 18. So therefore X is 14. So the area of the triangle with sides C, D, and 6 is 14. Okay, so that takes care of question 9. So you see, this is the solution that I had, which gives you the same solution. We can go on to the very last question. It's a long haul. So the last question reads the following. It is given that the sum of the infinite geometric series is 1. It's equal to 1. The infinite series is equal to 1. Now, you actually can prove this. The grade 11 and grade 12 people prove that this is equal to 1. So, here we are told that this is 1. That's good. We don't have to prove it. So this is equal to 1. One over 2 plus 1 over 2 squared plus 1 over 2 cubed. And when you add up all these, half and a quarter and 1/8 and so on, you're going to get 1. Okay, now they ask you they give you some other thing, namely 1 over 2 plus 2 over 2 squared plus 3 over 2 cubed plus 4 over 2 to the power of 4 plus etc. And what is this equal to? What is this sum? So let's call it X. Right? Now, when you do geometric sequences or series, a useful trick is to multiply throughout by the common ratio. See, what do you mean by common ratio is that each term here, 1 over 2 squared, is one half times the previous one. If you multiply this by half, you get this. If you multiply this by half, you get this. If you multiply by half, you get this. So that's what you call a geometric series, that each term in the series means sum, is one half the times the previous term. So we'll do the same thing for this funny looking sequence. We'll put x over 2 multiplied by half. And now let me just write down, I want to rewrite that original thing here. 1 equals a half plus 1 over 2 squared plus 1 over 2 cubed plus 1 over 2 to the fourth. And now I'm going to multiply this by half. Right? So you get x over 2. Now, when I multiply this by half, right, 1 over 2, it's going to be 1 over 2 squared. I'm going to put the 1 over 2 squared underneath here. Oh. And then when I multiply this by half, I get 1 over 2 cubed. Now this times half. The next one is 1 over 2 to the fourth. And so on. All right? Now I compare this with that one. Let me just knock this thing off so that you can see both of them together. If you look at this and compare it with the original one, you'll see 2 over 2 squared, 1 over 2 squared, 3 over 2 cubed, 1 over 2 cubed. Four over I should have multiplied this one here by a half. It's x over 2. So this is 2 over 2 squared. Sorry. This, oh, I'm sorry. I was wondering why this thing doesn't work. I'm multiplying x, that one there, by half. Okay, so I do have 1 over 2 squared. Now here I have, let's just take out all these. This was not correct. So I'm multiplying this by 1 over 2, and that's what I get. And here I multiply this by 1 over 2, I have 2 over 2 cubed. Multiply this by 1 over 2, I have 3 over 2 to the fourth. And so on. Right. Now if you compare these two and subtract them, you get x minus x over 2. Okay, the half remains solid. Now you got 2 over 2 squared minus 1 over 2 squared. That's 1 over 2 squared. I got 3 over 2 cubed minus 2 over 2 cubed. So that'll be 2 over 2 cubed. I got 4 over 2 to the fourth minus 3 over 2 to the fourth. That'll be 1 over 2 to the fourth. And what remains here is exactly what I had here. See? These two are exactly the same. And it was given that this thing here is equal to 1. So x minus half x is x over 2. This part is equal to 1. So therefore x itself, x over 2 is 1. So therefore x is equal to 2. And that is what we are aiming to calculate. Okay, so that takes care of 2024 junior team competition. Okay, so please look at the other ones that we have done in this series. 2023, if you haven't done so already, and 2025, and that will give you a good idea as to what the team competitions are all about. And there are some very searching problems in all of them. and hopefully you will have some ammunition to tackle rather difficult problems. But you must study these carefully and rewrite it yourself. Then only you will be able to learn mathematics. Okay, thank you very much for listening. And we now bring this session to an end.